This is lecture 3, and this lecture is about sterilization of fermenters and media. So why it is necessary? Why sterilization of fermenters and media is necessary? To avoid contamination. Because if our fermenter get contaminated, it can result in some dire consequences. So what kind of consequences? Such as, if our fermenter get contaminated with some for unwanted microorganisms, then the medium would have to support the growth of both the producer and contaminant organism, which will result in loss of productivity. And in case of continuous cultivation, continuous fermentation, the contaminant may outgrow the producer organism. Okay, and in case of biomass as product, the contaminant will result in total loss of product. Sometimes the contaminant microorganisms may produce some compounds which may make downstream processing difficult, and even sometimes the compounds produced by the contaminant may degrade the product. Okay, and in case of fermentation, when we use bacteria as a biocatalyst, if the fermentation gets contaminated with fuzz, more specifically, if the fermentation get contaminated by bacteriophage, it could result in the lysis of the culture. Okay, because we know bacteriophage, they infect and lyse bacteria. Okay, so now, how we can avoid contamination? To avoid contamination, we can follow certain ways. Like we should use pure inoculum to start the fermentation, and medium should be sterilized before using. Also, the fermenter need to be sterilized, and also sterilizing all materials to be added during fermentation. And throughout the process, we have to maintain aseptic condition. Okay, in addition, sometimes for some fermentation process, we can add an additional chemicals or substrates in the media. Which substrate will prevent the growth of all the other organisms except the fermenter organism, and this kind of fermentations are described as protected. For example, in case of brewing of beers, hop resins are used, and hop resins, they inhibit growth of most of the microorganisms. Okay, so in this case, if the fermentation is protected one, it's not necessary that we have to sterile everything. Okay, in that case, we just can maybe boil the medium and disinfect the fermenters, rather sterilizing it. However, most of the fermentation are not protected, so that's why sterilization is essential for most of the fermentation process. Okay, so how we can sterile, how we can sterile the media of the fermentation. Okay, so there are several methods. We can sterile by filtration, radiation, chemical treatment, heat. And out of these methods, heat or steam is the most useful method for the sterilization of fermentation media. Okay, so now filtration. When we will use filtration, uh, the fermentation media, they may contain several compounds which are heat labile. For example, certain vitamins, amino acid, proteins, they may get degraded if we try to sterile using heat. Okay, in this case, we should use filtration to sterile the media. And however, filtration has some disadvantages. For example, such as certain components of the nutrient solution may be adsorbed on the filter material, thus the filter may get clogged and sterilization process will be hampered. Okay, and for filtration, high pressures must be used, otherwise the media will not pass through the filter, and this is undesirable industrial practice. Industrial practice creating high pressure is undesirable. Then radiation. Many cellular materials Many cellular materials absorb ultraviolet light, leading to DNA damage and consequently to cell death. And wavelengths around 265 nanometer have the highest bacterial efficiency. X-rays are radiation, right? So X-rays are lethal and have penetration ability. However, these are costly. That means these are expensive, and also there are safety issue concerning the users. Like suppose I am doing the sterilization using radiation. So I if I get exposed to the radiation, that will be very harmful for me. Okay. So because of this, I mean safety concern and expensiveness, X-ray is not that widely used in the industry. Okay. Then chemical sterilizations. Several chemical, I mean not several actually, many chemical agents are frequently used in the industry, but mostly for disinfection. Okay, and the major antimicrobial chemicals agents that are used are phenol or phenol derivative compounds, alcohol, halogens, detergents, acid, alkali, gaseous, chemosterilizers, etc. Okay, so although chemicals agents are frequently used in the industry, they are mainly used for disinfectant purpose, not for sterilizing the media. Okay, because if we use chemical to sterilize the media, there can be residual. I mean, those chemicals, they can interfere with the quality of the media itself, and also the residual chemical, they may inhibit the growth of the fermentation organism. Okay, so that's why chemicals are not used to sterile the media. Okay, then heat sterilization. And this is the most, as I already said, this is the most useful method for sterilization of nutrient media. And when we will use heat to sterile, then we should keep certain factors in our mind, because these factors, they can influence the success of heat sterilization, such as the number and type of microorganism presents, the composition of the culture media, the pH value, and the size of the suspended particles. While vegetative cells can be easily killed at using relatively low temperatures, but in case of spores, much higher temperatures are required. Okay, even like we maybe a temperature as high as 121 degrees Celsius are required to kill the spores. Okay, and this table shows some example of cells and spores and required time and temperature to kill those cells or spores. Okay, such as vegetative cells. Okay, they are not that stable. I mean, if we use 60 degrees Celsius, vegetative cells will die, and also we don't need to heat for very long time. I mean, 5 to 10 minutes at 60 degrees Celsius will be enough to kill the vegetative cells. For fungal spores and yeast spores, a little higher, 80 degrees Celsius will be required, and we have to heat for 5 minutes. For general bacillus spores, 121 degrees Celsius for 5 minutes will be good enough. But while spores for bacillus stereothermophilus, we I mean for the spore of bacillus stereothermophilus, 121 degrees Celsius is used, but we have to heat for longer time, for 15 minutes. Usually it is regarded that the spores of bacillus thermostereophilus is the most resistant one. Okay, so that's why sometimes this spore is considered as a indicator organism for sterilization process. What I mean, suppose you have used a sterilization process to sterile the media or say the fermenter. Then after that, when you will evaluate it whether your sterilization process was successful or not, what you can do, you can check the presence of a bacillus stereothermophilus spore. So if there is no spore of bacillus stereothermophilus is there, you can confidently say that your sterilization process was successful. Okay, And however, it is please note that it is important to note that we are considering the number of organisms and not the concentration. And why number is important? Because there is a minimum number of organism which is required to contaminate the fermenter. Okay, so that's why most of the time number of organisms are considered when people calculate the conditions for the sterilization. Okay, so now for how longer we will uh, use the sterilization process. Okay, so it depends actually on the type of the population. Okay, so for example, you want to use heat sterilization, so for how long you will heat, it will depend on the type of the population of the organism. So if the sensitive organisms are more in number, then whole culture sterilization, then whole culture sterilization will be equal to that of the sensitive culture. Okay, however, if the number of resistance microorganisms is more, then the sterilization of whole culture is equal to that of the sterilization of the resistant organism. Okay, so I mean the time will depend whether there are more sensitive organism or more resistant organism. If there are more resistant organism, we have to uh, heat for longer time. Okay, so and also sometimes the contaminant may be uh, not a single type of organism. That means our farm there sometimes the contamination will be by several different kind of organisms. In that case, we have to consider all these organisms to design our sterilization protocol. Okay, now when we use temperature to sterile, okay, the temperature and time are inversely proportional, and same degree of sterilization can be achieved by varying time and temperature. So what it means, say you are using very high temperature, in that case shorter time will be okay, but if you use low temperature, in that case you have to heat for longer time. Okay, and in industry the accepted level of contamination is 0.001, that is 1 in on 1000 batches can be contaminated. After the process you use, if that process allow only 1 in 1000 batches to be contaminated, it will be accepted. Okay, now kinetics of sterilization. So why it is important to understand the kinetics or know the kinetics of sterilization. So suppose you want to use heat or radiation for sterilization, so you need to calculate that how much heat or radiation you will use and for how long. Okay, so if we want to calculate this, definitely we have to take help from the equations. So we have to use the equations of kinetics of cell death, and by using those equations we can calculate both the exposure amount at time required for successful sterilization. Okay, so in this chapter, actually we will not go for very detailed derivations of the equations. Rather, we will just try to see the equations that we can use to calculate the exposure time and amount for a sterilization process. Okay, so let's start. The process of destroying microorganisms is a first order kinetics and may be represented by this equation number 1, minus dn by dt equal to kn. Okay, here n is the number of viable organisms present, t is the time of the sterilization treatment, k is the reaction rate constant of the reaction, or the specific date. K is simultaneously it is the reaction rate constant, also it is the specific, it represent the specific date rate. Okay, so now if we do integration of this equation, it becomes like this: nt by n0 equal to e to the power minus kt, where n is the number of viable microorganisms present at the start of sterilization treatment. That means N0 is the initial number of viable organisms, and Nt is the number of viable organisms present after time t. Here t is the exposure time. So Nt represent the number of viable microorganisms after we finish the sterilization. Okay, so say for example you heat it for 10 minutes, so Nt will be the number of viable microorganisms after 10 minutes. Okay, now if we take natural log of equation 2, then it becomes ln Nt by N0 equal to minus Kt, and as with any first order reaction, the reaction rate increases with increase in temperature due to an increase in the reaction rate constant, which in the case of the destruction of microorganisms is the specific death rate. Okay, this is the characteristics of any first order reaction. So thus K is a true constant only under constant temperature conditions. Okay, now the relationship between temperature and the reaction rate constant was demonstrated by Arrhenius, and it may be represented by this equation: d ln K by dt is equal to E divided R t square. Okay, where E is the activation energy, R is the gas constant, and T is the absolute temperature. Okay, so now again if we take integration of this equation, then it becomes K equal to A e to the power minus E divided RT. Here A is the Arrhenius constant. Okay, now again if we take natural logarithms of this equation, equation number 5, it becomes like this: ln K equal to ln A minus E divided RT. Now if we combine equation 3 and 5, so equation 3 and 5, okay, so it becomes this: ln N0 by Nt equal to ATE to the power E divided RT. Okay, okay, so two scientists named, okay, actually this is the equation which we can use to calculate the required temperature, okay, and also the time. Now two scientists named De Indorfer and Humphrey, in 1959 they used this term ln N0 by Nt as a design criterion for sterilization, and which has been vigorously called del factor, nabla factor. Okay, and it is represented by this term, okay, del. So thus what del factor means: thus, del factor is the measure of the fractional reduction in viable organism count produced by certain heat and time organism, certain heat and time regime. So, for example, you have heated for 5 minutes at 110 degrees Celsius. So, how much how much organism will be reduced? Okay, so and we have to represent it as a fractional reduction, and this is del factor. So therefore del factor is ln N0 by Nt. Okay, but we already know ln N0 by Nt equal to Kt, and Kt is ATE minus E divided RT. Okay, so if we substitute this value in this equation, the del become ATE to the power minus E divided RT. Okay, so using this equation we can calculate the del factor. That means you can use different temperature, different value of temperature and different exposure time, and you can calculate what will be the del factor. That means in that temperature and time how much organisms will get reduced. Okay, so that's all for this part. In the next part we'll learn about the process by which we can sterile the media using heat. Okay, so thank you for your patience.